Continuing with our applications in physics and into engineering, we have force due to hydrostatic pressure. So it's fairly well known that if you dive down deep enough into a body of water, you will die a gruesome death because of the immense crushing pressure of the water. And the way this basically works is, suppose I had a plate. I'm going to do a triangle. So I'm going to make sure that this is a right triangle and the sides are the same length. So if I have a plate or a surface at a certain depth, I'm able to calculate the force exerted onto the top of this plate by the water. And this thought process is actually the way I prefer to approach the hydrostatic pressure problems, but there is another way where we deal directly with formula for pressure. So the area of this surface is, let's see, I gave that side lengths of 5, so it's 1/2 of 25, and we'll go ahead and say that that is in meters. So since it's at a certain depth, there is essentially a column of water sitting on top of this surface. So the volume of the water sitting on top of the surface is d times the area. So that's area of the base times the height of that column of water I have there. So d times 25 over 2. And this should be in meters cubed. So if I multiply by the density of water, I'll have the total mass of water, or the total weight of water if I add on 9.8. So the total weight of the column of water is going to be 9.8, which is gravity, times 1,000, which is the density of water in kilograms per cubic meter, times the volume of the water, and that is going to end up being in newtons. So that is the total force due to hydrostatic pressure on the top of this plate. Now I can calculate the pressure at this depth, but the pressure is simply total force divided by the area upon which the force is acting. So that appears to be 9.8 times 1,000 times d. So since the density of the fluid, be it a gas or a liquid, is going to be essentially constant, and the acceleration due to gravity is likewise going to be constant, unless you've got some really weird things going on. That means the pressure is simply a function of the depth in the fluid in which you are placed. So I'm going to try to do one of these where I think of it as pressure multiplied by area to get the total force. So the flat horizontal triangle I had before in the water was fairly straightforward, but what happens if I were to stand up that triangle? How would I find the total force due to hydrostatic pressure on this plate? Well, it's suddenly a more complicated problem because the force due to pressure depends on the depth, because the amount of pressure on an object is a function of how deep the object is. So I would have to so depending on how high up on my triangle I look, I'm going to have different amounts of pressure applied to that part of the triangle. But again, since pressure is only a function of depth, that means I'm going to, surprise, chop up my triangle at a bunch of different depths. So if I have a little strip of triangle, so if I go down to a depth of x, and I have a little strip of triangle of height delta x, then I can calculate the area of that strip. So how do I calculate the area of this strip at this particular depth? Well, I'm going to have to use similar triangles because I need to find out how long this strip is. I need to find out the width of that line. So if I'm at a depth of x, well, 4 of that is not a part of the triangle. So instead of having an x right here, I technically have x minus 4. That's how much of that distance is actually applied to the triangle, because 4 meters of that are above. But the total side lengths are still 5. So I have proportions. I have w is to 5 as, let's see, small to big. X minus 4 is also to 5, which implies that w is simply equal to x minus 4 for this problem. So the area of strip is w multiplied by delta x. Now the pressure on this strip is a function of the depth at which this strip occurs. So the pressure on this strip at depth x is rho gx, which is the density of the medium. I'm going to use water again, times acceleration due to gravity, which is 9.8, times x, and x is the depth. So the total force due to hydrostatic pressure on this strip is going to be the pressure multiplied by the area of the strip. So 1,000 times 9.8 times w, which is x minus 4. Oops. I need the x from the pressure times the x minus 4 from the w times the delta x. So that's my rho g. There's my depth. There's my width. And there's my height. So one of the possible ways to think about these problems is to try to calculate this right here, which is the volume of water above a strip. And maybe it's not a water, but it's a fluid of some sort. Both of these thought processes will get you to exactly the same place. So what I want to do to find the total force acting on my triangle is I'll just add up the force I calculated for all of the strips. So I have the sum from I equals 1 up to n of 1000, well, 9800 times x squared minus 4x times delta x. And these have little i's on them. But like in the previous sections, I should recognize this kind of a sum as an integral. So I would have an integral of the same term, 9800 x squared minus 4x times dx. But what are the bounds? Well, the depths at which I'm calculating forces occur from starting at a depth of 4, going all the way to the bottom of the triangle, which is 4 plus 5, so 9. So I calculate this for depths from 4 up to 9. So another situation we might have is a slanted plate, which works a little bit differently. Let's say I've measured the slant of this plate, and the slant occurs at an angle of theta. I'll make it a rectangular plate to keep things simple. Its width will be 6, and the height of the plate will be 4. So in complete terminology, a rectangular plate is submerged into a fluid of density ρ and is tilted to make an angle of pi over 3 with the horizontal. The rectangular plate's dimensions are as I've labeled in the picture. Now, if the top of the plate has a depth of 2 meters, we want to find the total force due to hydrostatic pressure acting on one side of this plate. So what we want to do is we want to set up bounds for x first. We want to find out how deep is this going to go. So if I look at this from the side, starting at 2, I have a tilt here. This length is 4, and this angle is pi over 3. Now I'm pretty sure I can do this with trig, because if I look at sine of pi over 3, this should be equal to opposite over hypotenuse. But the hypotenuse is 4. So this side here is equal to 4 sine of pi over 3. But sine of pi over 3, that is the square root of 3 over 2. This is equal to 4 times root 3 over 2, or 2 root 3. So the depth of my plate ranges from 2 to 2 times the square root of 3 meters. So I'll add that on here. Now what I need to do is determine the area of a strip at a depth x. So returning to my picture here, I'm slicing up my plate a bunch. And I want to find the area of a strip. But this little tilted triangle problem comes into play again. Because since my plate is tilted, if I'm looking at a strip here of delta x, that is not the length or the height of a strip on the surface. The delta x is a little change in height, but since the object is tilted, it's actually a little bit longer than delta x. So I have a similar little triangle set up here. here I have my pi over 3, except on this side I have my delta x. So what I'm looking for actually is like a delta s or something. This is actually very, very similar to doing arc length. And in fact, if I'm doing looking for hydrostatic pressure on an object which does not have a flat surface, and maybe it's curved or something, I would actually have to incorporate arc length or surface area somewhere in my integral. So sine of pi over 3 here is equal to delta x divided by delta s, or delta s is equal to delta x divided by sine of pi over 3. And you can use this in general. If I have a tilted surface, my delta s will be delta x divided by the sine of the tilt of the angle. So this is the height of the strip I'm supposed to have. What is the width of the strip? Well, fortunately I have a rectangle, so the widths of my strips are all 6 meters. So the area of a strip is going to be the width, which was 6, multiplied by the height, which is actually the delta s, which is delta x divided by sine of pi over 3. I should probably actually evaluate that. So this is 6 times 2 over root 3, because that's 1 over sine, times delta x. Or, let's see, if I rationalize this, I'm going to have 4 root 3. I'm going to have 4 root 3 delta x. So that's the area of my strip. And I just need to multiply this by the pressure that occurs at that depth. So the pressure at depth x, well, that's just simply rho. I'm going to stay on Earth, and then, well, it's just x that goes there. So, in my integral, I'm going to be looking at the integral from 2 to 2 root 3. Those are the depths at which my rectangle occurs. And I'm going to multiply the pressure by the area that it acts upon, which was 4 root 3 delta x turns into a dx in the integral. So here's my strip area, and here's my pressure. And I can go ahead and do this integral. This one's not too bad. This is p times 9.8 times 4 root 3 times the integral from 2 to 2 root 3 of x squared, of x dx, which becomes rho 9.8 4 root 3 times x squared over 2. There we go. 2 to 2 root 3. Why don't I cancel these 2's? So I have 2 root 3 squared, which is 4 times 3, which is 12, minus 2 squared, which is 4. So it looks like whatever I have is the density of the fluid times 9.8 multiplied by 16 root 3. And this is going to be in newtons. So the process of these is all basically the same. I'm going to go down to a depth x. I'm going to slice off a piece of whatever it is I'm trying to find out about, find the area of that slice, and multiply that by the pressure that occurs at the depth that the slice occurs, and just toss that into an integral. So a challenge I have for you guys is one of my favorite problems. It doesn't occur in the book, but suppose I have a sphere of radius r that occurs at a depth of d. My question is, how do I calculate the total force due to hydrostatic pressure on the sphere? Now, I'll go ahead and give you guys a hint. I'm going to have to take off a strip of my circle. But a strip of my circle, in order to calculate the area of that strip, I'm going to have to pull in some stuff from 8.2, because a circle is a surface area of revolution, if you think about it. So you have to carefully consider how to calculate the area of a piece, and you have to multiply the area of all those pieces by the appropriate pressure due to the depth at which those pieces occurs.